8.4 chain rule. This is one of our last derivative rules. Chain rule is used to, when you take the derivative of a composition of functions, so that means a function inside of a function. So here we have g inside of f, and in order to take the derivative, you take the derivative of the outside function, which is f, keep the inside function the same, and then you chain on the derivative of the inside function. So that's why it's called chain rule. Another way of looking at it is in dy over du format. So if we're finding the derivative of f of u, so u is the inside function, so you're going to take the derivative of the outside function with respect to u, so dy over du, times the derivative of the inside function with respect to x, so du over dx, and you multiply those together. So here is an example. If I want to find the derivative of 4x minus 9 raised to the 10th power. So this is our inside function, and our outside function is to the 10th power. So if you want to look at it in terms of u, we would say u is 4x minus 9, and f of u would be u to the 10th power. So you're going to find the derivative of y with respect to u. So that's using our power rule. We bring the 10 down and subtract 1 from the exponent, and that's where the 9 comes from. And then we take the derivative of u with respect to x. So we're taking the derivative of this function, which is 4. And then you're going to multiply those two together. So 10 u to the 9th times 4. So that gives you your 40. And then they went ahead and substituted u back in. So you get 44x minus 9 to the 9th power. So that's like the derivative of f, keep u the same, and chain on the derivative of u. Another way of looking at this, so if I have f of x equals 4x minus 9 to the 10th power, you don't have to rewrite it in terms of u. You can just take the derivative of the outside function, which is the 10. So I'm going to bring that 10 down, and I'm going to subtract 1 from the exponent. I keep the inside function the same, so the 4x minus 9 stays the same, but then I have to multiply or chain on the derivative of the inside function, which is 4, and then you can multiply that 10 times 4 to get 44x minus 9 to the 9th power. That's the way I normally do it. Okay, so let's go through some examples here. So our first example, when I see a constant on top being divided by a function, I immediately rewrite it using negative exponents. So I'm going to change this to t squared minus 1 to the 5th power. Sorry, to the negative 5th power, because we're moving it up. And then we're going to take the derivative using that chain rule. So my outside function is that negative 5th power. So I'm going to bring negative 5 down, keep the inside function the same, subtract 1 from the power, and then chain on the derivative of the inside. So the derivative of t squared minus 1 is 2t. And then I'm just going to simplify it. So I'm going to take this negative 5 and the 2t. I'm going to multiply those together to get negative 10t. And then I'm going to take the negative exponent and move it to the bottom to turn my exponent positive. And so that would be the final answer. Okay, example 2 is a little bit more complicated. It's going to take me a little bit more space than that. So I'm going to go to a different, so I have some more space here. Okay, so the big picture you want to see is that you have a function times another function. So I'm going to think of this as function A and this is function B. So when I find the derivative, I'm going to have to do product rule. But when I find these derivatives, they're also functions inside of other functions, so you're going to have to do chain rule. Okay, so your big picture, so we're going to find the derivative of f. So I keep the original, that first function stays the same, times, and then I have to do the derivative of b. When I do derivative of b, I bring that exponent down, keep the inside function the same, subtract 1, but then I have to chain on the derivative of the inside function, which is 4. Then plus, now I have to find the derivative of a. So I'm going to bring that 3, the exponent of 3 down, keep 2x minus 1 the same, subtract 1 from the power, and chain on the derivative of the inside function. So derivative of 2x minus 1 is 2. And then times b, which is just bringing that second function down. So again, what I did, this is the a. All of this is b prime. All of that is a prime, and this is b. So you're just doing product rule. And now we have to do a lot of simplifying. So what I'm going to do is I'm going to look at this first expression and this second expression. They're separated by a addition sign. So we're going to look for things that are in common in each of those yellow terms. So, and we're going to factor out that GCF. So when I look at first, if I look at the numbers, I see a 2 and a 4 in that first yellow term, and then I see a 3 and a 2. So my GCF would be a 2. So I can take out a 2. Then I see that there's a 2x minus 1 and a 2x minus 1. So I can take out 2x minus 1. And then I'm going to look at the exponent and see that I can take out 2 of them. They have 2 in common. Then I see 4x plus 2 in common to each thing. So I can bring out a 4x plus 2. And again, when I look at these exponents, the lowest exponent is 1, so I can only take out one of those. So that's my GCF, and now I'm going to see what I have left after I factor it out. So I took this 2 out, so I still have a 4. 2x minus 1, I took 2 of those out, so I am left with 1, 2x minus 1. The 4x plus 2 is gone, so then I have my plus sign. I took this 2 out, so I have a 3 left. 2x minus 1, I took both of those out, so those are gone. And then the 4x plus 2, I took one of those, so I have 1 left over. And now we have to take the inside right here, and we have to simplify that. So we're going to like distribute this 4, distribute that 3. I'm just going to write it under here. So this would give me 8x minus 4. And here I'd have 12x plus 6. And we're adding those. So my final derivative here. So my GCF was that 2x minus 1 squared 4x plus 2. And now instead of hard brackets, I'm going to change it to parentheses, and I'm going to combine my like terms. So 8x plus 12x is 20x, and negative 4 plus 6 is 2. And now that is a fine answer, but there could be a chance that they factored it a little bit further because there's a GCF there and a GCF there. So they could have taken a 2 out here and a 2 in the next parentheses. So now we have this 2 times 2 times 2, which would give us 8. And then 2x minus 1 squared, 2x plus 1, and 10x plus 1. So that's just even more simplified, but either one would be fine. Okay, now our next example, example 3. So again, I have a function times another function. So I'm going to rewrite that using fractional exponents. So when I go to find the derivative, so I'm going to call this dy over dx this time. I'm going to have to do product rule. So if this is a and this is b, we're doing a times the derivative of b plus derivative of a times b. So I keep that x squared times, now the derivative of b, we bring the 1/2 down, subtract 1, times, we have to look inside and find the derivative of 1 minus x squared, which would be negative 2x, plus the derivative of a, which is just 2x. There's no chain rule. There's no function inside of a function. And then times b. All right, so now this one is a little bit different. Instead of factoring out a GCF, since we have some negative exponents, here's one term and here's our second term. Since we have negative exponents, I'm going to choose to rewrite this and into fractions and then get a common denominator. Now you could factor out a GCF, but we'd be factoring out a negative exponent. So let's see, right here I have an x squared, I have a 1/2, and I have a negative 2x. So since all of these are being multiplied together, we can multiply those three terms. So like if I go off to the side and I multiply x squared times 1/2 times negative 2x, that's going to give me negative x to the third. So here I'm going to have negative x to the third. And then I'm going to move that exponent down to 1 minus x squared to the 1/2. Plus, and then I have 2x 1 minus x squared to the 1/2. And I might actually, let's change those to square roots instead. So negative x. Okay, so now we need to add these two fractions. So this denominator right now is a 1. So this denominator needs a square root of 1 minus x squared, which means the top needs the same thing to keep it balanced. So now my denominators match. This denominator and that denominator match. So I can rewrite that as one fraction. And then this numerator plus, and what's going to happen here is if I multiply two square roots that are the same, the square root just goes away. And now it's just a matter of distributing and combining like terms. So negative x cubed and then I have those x cubes that I can combine. So negative 3x to the third plus 2x all over the square root of 1 minus x squared. Now, we could rationalize that denominator too. You can leave it like that. Or if they had it rationalized, it would look like this. So that's what it would look like if we rationalized. Okay, now example 4. So now the big picture is quotient rule. So we're going to have to do quotient rule. So again, I'm going to rewrite this using fractional exponents. And now we're going to be doing low d high minus high d low all over low low. So our derivative. So low is our denominator. D high means derivative of numerator. So derivative of x is just 1. Minus high, which is our numerator, which is x, times derivative of the denominator. So that one's a little bit harder. We bring the 1/3 down, keep our inside function the same, subtract 1, but now we can't forget to look inside and multiply by the derivative of the inside function, which would be 2x. And then it's all over low, low. So the denominator, oops, squared. Okay, so again, low, d high minus high, d low, all of that stuff is d low all over low, low. So here, again, we have some ugly looking stuff. We have to get rid of our negative exponents. We have this term, and that term that are all being multiplied that we can write as a single term. So let's see, I'm going to get rid of that 1. So I'm just going to write this as x squared plus 4 to the 1/3 minus, now those things in yellow, I'm going to go ahead and combine. So that's going to give me 2/3. And then x times x is x squared. So I'm going to write that on top. And then I'm going to take this term right here that has that negative exponent, and I'm going to move it to the bottom. So I'm just going to kind of extend this fraction bar, and I'm going to move that x squared plus 4 and make it to the 2/3 by moving it to the bottom. Now you can only, this here is one term, and this is another term with a subtraction in between. So this denominator cannot, this term right here cannot just go down with that bottom. You cannot do that because of this subtraction sign. So that we still have this all over low, low. And I'm going to go ahead when I have a power to a power, I multiply. So that's going to give me to the 2/3. And now I have a little fraction inside of a big fraction, so we have to get rid of those denominators. So I'm going to multiply the top by my common denominator, which is, and that's really over 1. And whatever I do to the top, I have to do to the bottom. So you're going to take this expression and you have to distribute it to that term and to this term. So when I distribute, I get 3, and then that times that, you just add the exponents. So x squared plus 4, and 1/3 plus 2/3 is just 3/3, which is 1. Minus, when I distribute the second one, the whole denominators are going to wipe out, so I'm just left with 2x squared. And then on the bottom, again, when we multiply, we add exponents. So 2/3 plus 2/3 is 4/3. And now I can distribute this 3. And combine like terms. So my derivative will equal x squared, because 3x squared minus 2x squared plus 12 all over 3. That would be our final answer. Okay, so that was 4. All right, example 5. We could do just chain rule and quotient rule inside, but I prefer to rewrite this as just squaring the top and squaring the bottom, and then doing quotient rule. So again, we're going to do low d high minus high d low all over low low. So my derivative, okay, so low d high. So again, we're going to have to do chain rule. So we bring the 2 down, keep the inside, subtract 1, chain on the derivative of the inside. So low d high minus high d low. So bring the 2 down, subtract 1, and chain on the derivative of the inside. So derivative of x squared plus 3 is 2x, and it's all over low, low. Okay, so now I'm going to look to see what I have here. So I have all of that's being multiplied. All of this is being multiplied. It's separated by a subtraction sign, and my bottom, so we can simplify as long as we have things in common in each of those blue highlighted areas. So I see an x squared plus 3, an x squared plus 3, and an x squared plus 3. And I see that they have 1 in common. So actually, before I do that, let me change this to the x squared plus 3 to the 4th power, just multiplying those. Okay. So now let's cancel out. We can cancel out, like I said, what we have in common, the x squared plus 3. So I have 1 here, so I'm going to change this exponent from a 2 to a 1. That is just going to wipe out, and I'm going to change this exponent to a 3. So let me rewrite here what I have. So x squared plus 3. I'm going to go ahead and multiply 2 times 3 to get 6, and I'm going to put it in front. I have a 3x minus 1 minus, again, I'm going to take this 2x and 2, and I'm going to multiply those to get 4x. I have 3x minus 1 squared all over x squared plus 3 to the 3rd power. And this does not have any negative exponents. So what I'm going to do next is I'm going to factor out a GCF from top. So I'm looking at these 2 expressions in yellow, and I'm seeing what they have in common. So I see that they have a 2 in common, and then they have a 3x minus 1 in common. So when I take that out, I'm going to be left with 3 x squared plus 3 minus 2x and 3x minus 1 all over x squared plus 3 cubed. So again, I looked at, they had this and that in common, so I only took out 1. They also had 4 and 6, which could both be divided by 2. So now, sorry. Now I need to clean up the inside this bracket. So like distribute this, distribute that, and combine like terms. So don't forget we're distributing in negative 2x. And now we're just going to take that stuff and clean it up. Would be our final derivative. Okay, so things to keep in mind when they ask you to find the derivative and simplify. Pull out GCFs, no negative exponents, no radicals in the denominator, and make sure fractions are added together. All right, moving on to trig. So chain rule for trig means that usually we have a function inside of the trig, which means it's like the angle part of it. So if we're finding the derivative of any of our trig functions, it's the same derivative rules. It's just chaining on that derivative of the inside function. So derivative of sine is still cosine, but you chain on the derivative of that angle. Derivative of cosine is negative sine. Keep the angle, but you chain on the derivative of the angle. And usually when we chain it on, we actually move it in front of the trig. All right, so if I want to find the derivative of sine 2x, so that's like in parentheses here. So I find the derivative of sine is cosine. You keep the inside function the same, but then we chain on the derivative of the 2x, which is 2. But instead of writing it like that, we're going to write it as 2 cosine 2x, and that's it. Okay, so the next one, derivative of tangent. So the derivative of tangent is secant squared. You keep that x minus 1, but then you chain on the derivative of x minus 1, which is just 1. So you don't need to write the times 1, but we can. So I'm just going to erase that times 1. Okay, the next one, so this is like in parentheses like that. So if we want to find the derivative of secant, the derivative of secant is secant, keep the angle, tangent, keep the angle, times the derivative of this 3x squared. So the derivative of 3x squared, bring that 2 down and subtract 1 would give 6x, and I'm going to write it in front. So again, the derivative of secant u, if that's my function, the derivative is secant u tangent u times the derivative of u. So that's what we're doing here. So we have secant u tangent u derivative of u. Okay, here the parentheses are in a different spot. So this is actually a constant times a function. So this derivative is just going to be bring this 2 down. So 2 cosine 3 and subtract 1 from the power. So that would just be your derivative. 2 cosine 3 times x. So if we move the parentheses, that changes it. So if I move the parentheses, now this is u. So if I'm finding, if I have cosine u, the derivative is negative sine u times u prime. So this derivative is going to be negative sine u, so I keep the 3x squared, times the derivative of u, which would be 6x. And again, instead of writing it like that, I'm going to move the 6x in front of the sign. Right, now we have double chain rule, which sometimes we say ETA, which stands for exponent, trig, and angle. Another way of looking at it is a function inside of a function inside of a function. So we have u, which is a function, inside g, and which is also inside f. So you take the derivative of the outside function, you keep the inside function the same, times the derivative of the inside function, keep the inside function the same, and chain on the derivative of the innermost function. Or you can think of it as you finding the derivative, first doing the exponent, then doing the trig, then doing the angle. So let's see. So this function I'm going to actually rewrite as cosine 4x, the quantity squared. So you can kind of see that this is my innermost function. Then I have the trig function, and then I have the exponent. So you have a function inside of a function inside of another function. So if I go to find the derivative, I start with the outermost function, which is the exponent. So you bring the 2 down, and we do nothing to the inside functions. We subtract 1 from the power, times, now we do the next inside function, which is the trig. So we're doing e, which is exponent. Now we're going to deal with the trig. Derivative of cosine is negative sine, but we're still keeping that 4x the same. Now we deal with the angle, which is the 4x. The derivative of the angle is 4. And now I don't like the way that's written. I'm going to take this 2, this negative sign, and the 4 and combine them. So the final answer would look like negative 8 cosine 4x sine 4. Right. Now this next one here, I'm going to rewrite again as sine 4t all to the third power. That just helps me to see that it's chain rule. So when I go to find the derivative, again, I do e, which is angle, times derivative of the trig, derivative of sine is cosine, times the derivative of the angle, which is 4. So this answer would be 12 sine 4t cosine 4t. All right, I think this is our last example. So this one, again, you have to look at the big picture, which is product rule, 2 functions being multiplied. So we have to do a b prime plus a prime b if this was a and this is b.